Hello everybody and welcome to exercise 1. We are looking at the top of page 41 in the workbook here. And here's another problem involving directional derivatives and gradients. Let's take a minute to read this together. So we've got a heat source that's lying at the origin of the xy plane, and they're giving us a function that represents the temperature at any point in the plane, and our distances are being measured in meters. Okay, and they're going to ask us to calculate and interpret some quantities here. So let's start with part A. They'd like us to calculate the gradient of t at the point 1, 1. Okay, and we know that the gradient involves partial derivatives. So we're going to have to take our function and take some partial derivatives, and it's convenient before we take the derivatives just to rewrite this. Okay, as it is, t of xy is in the form of a ratio. It's more convenient to move that denominator up into the numerator. We can do that by rewriting the function like this. It's equivalent to 100 times 1 plus x squared plus 2y squared to the negative 1. Okay, so with that cosmetic change, let's go ahead and calculate our two derivatives. So the derivative in the x direction, looking at our formula, we're going to use the power rule and the chain rule. So taking the derivative of something to the negative 1 power, that negative 1 is going to come down. We're going to get negative 100, 1 plus x squared plus 2y squared to the negative 2. But then the chain rule says we need to multiply by the derivative of the inside with respect to x. And that derivative is going to be just 2x. Okay, because the 1 and the 2y squared, those just involve things that we're treating as constants when we take the derivative with respect to x. Okay, and ty, very similar calculation. So if we use the power rule there, it's going to start off the same way. Now we're going to be multiplying by the derivative of the inside with respect to y. That's going to give us a 4y. Everything else is going to go to 0 when we take that derivative. Okay, and so the gradient of t, by definition, has it as its components these two partial derivatives. So this is going to be kind of long because these derivatives are long formulas. So let's just write it out. Negative 100, 1 plus x squared plus 2y squared to the negative 2 times 2x. All of that is our I component plus negative 100, 1 plus x squared plus 2y squared to the negative 2 times 4y. All of that's our j component. Okay, that is a long formula. Okay, and so to make our calculations a little bit easier, we might notice that there's a term that's common to the I and the j component, so it might help us just do things a little bit more quickly if we factor that out. So I'm going to take that underlined portion and just factor it out. Okay, and what's left is 2x in the I component and 4y in the j component. Okay, there's a more simplified formula for the gradient. All right, so I think we're ready now that we have a formula to do the calculation of the gradient of t at 1, 1. Okay, that's just a matter of taking x equals 1 and y equals 1 and substituting into this formula that we just found. Okay, so we'll take negative 100. If we plug in x and y both to be 1, we're going to get a 4 to the negative 2. And then we're going to get a 2i plus a 4j over here. Okay, if you take this number out front and just distribute it through, you can simplify this gradient vector down to the following. Negative 12.5i minus 25j. You can double check my calculations. Okay, so we have finished the first part of this part of the exercise. We calculated the gradient of t at 1, 1. Okay, but they also would like us to explain what it means, give a practical interpretation. So what is the gradient telling us? Okay, the gradient tells us the direction that we need to move in to get maximum temperature increase. Okay, so let's try to put that into words here. So this means that So we need to move away from the point 1, 1. That's our starting point here. In the direction negative 12.5i minus 25j. To experience the maximum rate of temperature increase. Okay, so it just gives us a direction to move to get warmest fastest, basically. Okay, and so next, part B asks us to calculate the magnitude of the gradient. Okay, and the nice thing here is we've already calculated the gradient, so all we need to do for the computational part is to take its length. All right, so let's see, the length of that vector is going to be the square root of the sum of the squares of the components. Okay, and you can punch that into your calculator and confirm that we get about 28.0 if we round it off to 1 decimal place. And what does that number mean? Okay, that's part of our answer. Okay, well, the magnitude of the gradient, remember, gives us the magnitude of maximum temperature increase. Okay, so it's telling us how fast the temperature is changing if we choose to move in the direction of the gradient. Okay, so let's see if we can put that into words. So if we move away from 1, 1, in the direction of the gradient, the temperature increases at a rate of 28, but what would the units on that be? Okay, so how are we measuring temperature in this problem? Okay, you can look up and notice that our units for temperature are degrees Celsius, and our distance units are meters, so this should be degrees Celsius per meter. Okay, that's the actual units on the rate of change. Okay, good. So we've got a calculation, we've got an interpretation, and we're ready to move on to the last part of this. Okay, so in this part, they're giving us a vector u. You might notice that that's a unit vector. You can check that by direct calculation. And they'd like us to calculate t sub u at 1, 1. Remember, that just means directional derivative of our temperature at the point 1, 1. Okay, so formula for the directional derivative is just to take the gradient and to dot it with u, the unit vector. And we've already calculated the gradient and even used it a couple of times. So the gradient at 1, 1 is just that. So that's the first thing we're going to write down. Okay, we'll take that and dot it with u, 2 over the square root of 5i, plus 1 over the square root of 5j. Okay, go ahead and do the dot product. So we're multiplying coordinates together. Okay, notice we've got 2 minus signs there, so we're going to get a negative answer. And if you substitute that all into your calculator, you are going to get negative 22.4. Okay, this is a rate of change again, so we can even put units to that of degrees Celsius per meter. Okay, so there's the first part of our answer. We calculated the directional derivative. What would be an interpretation of this? Okay, well, that's just giving us a rate of temperature change as we move away from this point in a particular direction. Okay, so let's put that into words. Okay, so the temperature decreases because of that negative sign at a rate of 22.4 degrees Celsius per meter as we move away from the point 1, 1 in the direction of u. Okay, And if you want to maybe get a little graphical insight into this problem, we could go back up to the level curves diagram and maybe just sketch in this vector u. Okay, so we're starting from the point 1, 1, that's here. And u, if you get decimals for the x and the y component, you'll discover that it looks roughly like this. And so ask yourself, does it look like the temperature should be decreasing as we move in that direction? Kind of does, because we're sort of starting near the contour of 30, we're moving through the contour 15, that's a decrease in temperature, so it kind of makes sense that our answer to the last part should be negative.